Okay, everybody, welcome to this Earth-to-Earth seminar today. Just to remind you all, Earth-to-Earth is a fortnightly seminar series organised by a consortium of UK universities in collaboration with Nature Geoscience and the British Geological Survey. Any UK institution that would like to have a representative on the governing board but doesn't have one at the moment should contact us by email. And further details about this seminar series are available on our website at earth2earthseminar.com. The mission of Earth2Earth is to engage the UK geoscience community with inspiring science from internationally leading researchers, and to do this whilst also promoting inclusivity and diversity, supporting the advancement of early career researchers, and highlighting the ways in which geoscientists can contribute to addressing global environmental challenges. Earth-to-Earth seminars take place every 2 weeks at this time, 3 p.m. in the UK, and they're open to everybody. You can watch our seminars either via Zoom or via live stream on YouTube, and all of our seminars are recorded and with speaker permission made available on our YouTube channel, along with closed captioning a few days later. Details of future seminars are available also through our website via the calendars page. During seminars, we ask that you all follow our code of conduct, which again you can find on the website. Questions, if you wish to ask them, will be answered hopefully by our speakers at the end of their presentation, and you can put them down in the Q&A section of the Zoom window. If you're watching on YouTube, please put any questions in the comments section there, and one of the governing board will transfer them across to Zoom for answering. Now, it's my pleasure to introduce our speakers for today. And we're very fortunate to have Laura Wallace and Emily Warren-Smith joining us from New Zealand. Particularly fortunate given it's currently 4 a.m. in New Zealand, so thank you very much to them for joining us. So Laura Wallace currently holds a joint position between the University of Texas Institute for Geophysics and GNS in New Zealand. And in 2018, she was elected as a Fellow of the Royal Society of New Zealand. Our second speaker, Emily Warren-Smith, is a seismologist and is also at GNS in New Zealand. And today they're going to be talking us through putting a finger on the pulse of slow motion earthquakes. Laura, take it away.
Great, thank you, Tim. Thanks for having us come in and speak for your seminar. I've already had about at least one cup of coffee, so hopefully can get through this. So Emily and I are going to talk a bit today about some work that we're doing to try and understand these slow motion earthquakes or slow slip events, particularly focused on the ones that we see in New Zealand. Let's see. There we go. It's slides advancing now. Before I get into this, I want to acknowledge there's a lot of people involved in the work that I'm going to be talking about today. These are just a few of them. But there's really many others that are involved in the work that we're trying to do to understand these slow slip events in New Zealand. So just to give you guys some context for the subduction zone we're going to talk about today, since all of you might not be familiar with it, we're focusing on the Hikarangi Trough, and that's located offshore the east coast of New Zealand, and it's accommodating westward subduction of the Pacific Plate beneath the eastern part of the North Island. The Hikarangi Trough actually links up further north with the Kermadec Trench up here, and that continues further north to the Tonga Trench. So it creates one of the longest sort of contiguous subduction systems in the world. But we're really going to be focusing today on the southern end of that system, the Hikarangi subduction zone. At this subduction zone, the type of crust being subducted is not really normal oceanic crust. It's the Hikarangi Plateau, which is actually a Cretaceous oceanic plateau. It's a large igneous province, so it's slightly over-thickened relative to normal oceanic crust. From a monitoring standpoint and an ability to investigate the subduction zone, this is actually very fortuitous, because as you're trying to subduct this slightly over-thickened crust, it serves to really jack up the forearc of the subduction zone, so that we actually have land above parts of the subduction zone that are normally well offshore. And this really enables us to be able to leverage land-based monitoring of a large portion of the plate boundary with things like GPS and seismic networks. Just for context, along the east coast of the North Island, the subduction interface is only about 12 kilometers depth. At many other subduction zones, that's equivalent shallow portion of the plate boundary is 50 or 100 kilometers offshore. So in some ways, we're kind of lucky here. So slow slip events, since this is a fairly general audience, a lot of you might not know what slow slip events are. So a slow slip event is really similar to an earthquake. An earthquake involves meters of movement along a fault in a matter of seconds. A slow slip event is essentially a slow motion earthquake that typically involves centimeters to tens of centimeters of movement along the fault over a period of days to weeks to months and sometimes even years. It's really only been in the last 15 years that their existence has become widely recognized, and that's largely because of the advent of continuously operating global positioning system networks around the world. And these GPS networks allow us to look at these sort of subtle changes in movement of the land related to these slow motion earthquakes. The map up on the right is just showing some of the locations where slow slip events have been observed. They've been most widely observed at subduction zones. I would say pretty much almost every subduction zone that has GPS instrumentation and the ability to look at these things, they've been seen, but they've also been observed on other types of faults like the San Andreas fault and various other types of faults. So what we look for up here in the upper left, this is just a time series. These are actually from some continuous GPS sites in the east coast of the North Island. And what we tend to look for is this sort of sawtooth pattern. And because in between this slow slip events, you have sort of locking on the plate boundary and the land gets pushed, in this case, westward in the New Zealand case. And that's this downward movement. This is the east component of motion. And then when the slow slip event occurs, the land slowly bounces back to the east. So we see this eastward motion every now and then at our GPS sites in New Zealand. And this similar type of displacement pattern is also seen at other subduction zones like Cascadia and Japan and elsewhere where they observe these slow slip events. That's the sort of really widespread recognition of slow slip events has really opened our eyes, first of all, into the fact that slow slip events appear to play a pretty major role in the accommodation of plate motion at subduction zones. And the discovery of these things has really opened our eyes to the spectrum of slip behavior that occurs on faults. We now realize that faults don't just either creep steadily or slip, lock up and slip suddenly in earthquakes. There's actually a whole spectrum of different types of slip behaviors on these faults. And they're also really important to be understanding from a seismic hazard point of view. For example, the magnitude 9 earthquake in 2011 in northern Japan appears to have been preceded by a large slow slip event, and it's possible that it was actually triggered by a slow slip event. So we also really need to understand the role these things play in sort of seismic, potentially damaging earthquake occurrence and their relationship to earthquakes. And that's something that's very important to understand from a societal and hazard point of view. So just to get into what we see in terms of slow slip events at the Hikarangi subduction zone, we see kind of lucky here too, we see a large variety of different types of slow slip events happening on the Hikarangi subduction zone. I'm going to show you a couple of the two sort of end member examples. This figure on the left, again, these are the GPS time series. This is from about a 10-year period, or maybe longer. I can't read, about 12 years here. And these are showing daily positions of these GPS sites. And you can see that westward movement between the events, and then you see the abrupt eastward movement during the slow slip events. So these are these highlighted time series on the left are from sites along the east coast of the North Island, and these are related to slow slip events happening offshore off the east coast. And these events, as you can see in the time series, are happening pretty frequently, particularly up in this northern half of the slow slip area. Probably at least every 1 to 2 years, and sometimes even more frequently. And they're also quite large. They tend to involve about 3 to 4 centimeters in some cases of surface displacements. And they're fairly short, typically lasting maybe a few weeks or up to a couple of months. And they're happening at shallow levels on the subduction zone. These are the contours of the depth on the right. The dashed black lines are contours on for the plate interface depths. You can see they're largely happening at sort of shallower than 10 to 15 kilometers. In the south, we actually see a very different situation. These highlighted yellow time series are from GPS sites down in this area at the southern part of the Hikarangi subduction zone. The red contours are showing our deep slow slip area, and that's these time series are from these deeper slow slip events that are happening at sort of greater than about 25 kilometers on the plate interface. You can see that the slow slip periods are much longer. They tend to last about a year to a year and a half, and they're also much less frequent. They tend to occur around every 5 years or so in these deep slow slip areas. And they're also, again, quite large slow slip events. They tend to involve about 3 or more centimeters of both horizontal and vertical surface displacement. So these are really large slow slip events to compare to other pretty well-known slow slip areas like Cascadia. The slow slip events in Hikarangi tend to be about 10 times larger than the Cascadia slow slip events. I also want to point out the black dots are showing the location of our continuously operating GPS sites operated as part of the GeoNet network. All of that data is publicly available on the GeoNet website. Today, though, we're going to really focus on these shallow offshore slow slip events. We've been putting a lot of effort into this area, and part of the reason to focus on these shallow slow slip events is that because we can do very near field observations, both geodetically and with seismic deployments, and also seismic imaging, and even using scientific ocean drilling to investigate them, because we can get so close to them that this offers a really unique natural laboratory to try and better understand some of the processes behind these slow motion earthquakes and why they happen. So toward that sort of end, as you can imagine, with these slow slip events, this is a zoom in on the northern part of the Hikarangi margin up here. As you can imagine, the slow slip events are largely happening offshore. It's very difficult to say much in detail about the slip distribution by using only land-based continuous GPS. So to that end, we decided to try and see if we could look at these things with seafloor geodetic techniques. So in 2014, we undertook the Hobbits Experiment. In mid-2014, we deployed 24 seafloor pressure sensors, and that's the seafloor geodesy part. We also deployed 15 ocean bottom seismometers. The way that you can use seafloor pressure sensors to try and understand the deformation of the seafloor during these slow slip events is we can actually detect the vertical deformation with these things. And that's because if you can imagine, a slow slip event occurs, if it causes uplift of the seafloor, you have less water above you and you record a pressure decrease. Likewise, if you have subsidence during the event, you have more water above you and you record a pressure increase. And the ocean bottom seismometers are obviously to get at more details on where the seismicity related to the slow slip events is occurring. And Emily is going to talk a lot more about that in her the later part of this seminar. And this is an internationally collaborative project involving PIs from the US, Japan, and also New Zealand. We were lucky during the deployment, the Hobbits deployment. In the middle of the deployment, sort of in late September, early October of 2014, we actually had a large slow slip event recorded by GPS sites on shore. These time series from the GPS are shown at the bottom here for these two sites. And then above on this lower left, these other time series are seafloor pressure time series during this period. And you can see at a lot of the seafloor pressure sensor sites, so pressure is decreasing as you go up on the y-axis here. And so this is looking at it in terms of pressure change in terms of equivalent change in elevation of the seafloor. So you can see from before to after the slow slip event, these sites above the slow slip area underwent a pressure decrease. Sometimes, really on the order of about 1.5 to 5 centimeters of vertical deformation of the seafloor. So this allowed us to better constrain the slip distribution during the slow slip event offshore. So we inverted the offshore vertical displacements from the seafloor pressure sensors and the onshore displacements from the continuous GPS network. And this is a slip distribution we published a few years ago. There's been a few more papers come out since really refining that. But what we found is in terms of the slip, so this is about 20 centimeters of slip on the plate boundary at about 5 to 7 kilometers depth. So that was kind of where our peak slip was. And the sites near the trench, for example, these sites here seem to show, about 1 to 2 centimeters of vertical deformation, suggesting that the slow slip potentially went, to within 2 kilometers of the seafloor and possibly even all the way to the trench. So this really helped us to constrain also that trenchward extent of the slow slip, which we really constrained with the onshore GPS data. So since the Hobbits experiment, we've been getting more of these pressure sensors out on different experiments. We did a experiment extending further along the East Coast. So the Hobbits experiment was really focused on this area, this small area up here. Sorry. In late 2018, we did another deployment that continued further south of seafloor pressure sensors. And we also had some ocean bottom seismometers out. I think Emily might talk about that as well during this event. But again, in the middle of the event, we were also very lucky. We had a very large, or in the middle of the deployment, we had a very large slow slip event. You can see in the GPS time series here that extended beneath this offshore region, beneath our deployment area. And again, in this event, we're looking at some sites in terms of horizontal displacements, on the order of 3 or 4 centimeters. So really quite a large event. And again, this was a very collaborative project. We have a lot of folks involved in this experiment. And on the right is just showing the distribution of seafloor pressure sensor sites we use. Okay, so I'm going to show, this is just a time-dependent, this is a preliminary time-dependent model constrained by the onshore GPS time series and the seafloor pressure sensor time series from our PhD student, Catherine Woods at Victoria University, who's working on this. And she's actually going to be giving a talk for AGU. So if you're interested in getting more details on this work, I definitely go try and check out Katie's talk. But I'm showing here the slip, weekly slip, and this is the time series. Sort of as this slip evolves, the blue are a subset of the seafloor pressure sensor sites, and the red are a subset of the continuous GPS sites. And you can see in the blue, we see vertical deformation, for example, at this site, this seafloor pressure sensor site, on the order of a few centimeters, and at this site and also the sites around it on the order of a couple centimeters during the event as well. So just a little bit about the details of the event, and also the dots or the seismicity occurring during the event, which Emily might talk a little bit about later. The event, let's say till the movie starts again. The event started in late March. So if we go again up here, and this was in the Hobbits deployment area, and then it spread out to the south off Hawke's Bay. And then later in the event, and this is particularly constrained by the seafloor pressure sensors, the slow slip event appeared to migrate up dip towards the trench off the Hawke's Bay region. This is an area, this offshore Hawke's Bay area is an area where we hadn't had previous seafloor sensor deployments. And so this really provides some new and unique insights into the slow slip event behavior offshore this area. This is where the land is the furthest from the trench and where we have the least constraint from GPS. Okay, so this figure on the right is the total slip for that particular slip model during the 2019 slow slip event. And also I'm showing here the location of some past subduction earthquakes inferred both from the historical earthquake record. In 1947, we had 2 roughly magnitude 7 earthquakes on the which we think are on the offshore plate boundary. And those actually, we call those tsunami earthquakes because they generated much larger tsunami than you would expect from magnitude 7 earthquakes. And this coastal area just to the west, these earthquakes involved about 8 to 10 meter tsunami. And then from paleoseismology, there's evidence along this coastline at various paleoseismic sites for quite a large number of abrupt subsidence events preserved in the sedimentary record over the last 7,000 years, which indicate potential rupture of the subduction interface right out here offshore Hawke's Bay. And this is also in the heart of that slow slip area. So I think this co-location of these shallow slow slip events in these past earthquakes really highlight the possibility that these slow slip event regions are not necessarily just happily, episodically slipping without large earthquakes. It's possible that they can also host seismic rupture. And this has some important seismic hazard and tsunami hazard implications, and that we really do need to be considering these shallow slow slip event regions also as sources of seismic rupture as well. And particularly these tsunami earthquakes, which similar to those that happened in 1947. So one of the big questions, so we see a lot of the evidence for slow slip events in New Zealand on the Hikarangi subduction zone. But one of the big questions is what causes slow slip events to occur? And in this case, what is causing this very shallow slow slip that we see at the northern Hikarangi subduction zone? Some of the characteristics of the plate boundary in this area, there's quite a lot of geometric roughness. There's things, this is a Turanganui Knolls seamount that's protruding above the sedimentary cover. We see quite a large number of these seamounts on the incoming plate. So it's a fairly rough incoming plate. So there's, the likelihood that some of this geometric heterogeneity may cause a very heterogeneous distribution of stresses on the plate boundary and promote this transient slow slip behavior. And it also may promote a more melange-like plate interface with a mixture of different types of lithologies. You can also see here, this white contour is a seamount that's been inferred from magnetic anomalies and also seismic reflection data. This is the interpretation of the top of the seamount from the seismic reflection data that's also embedded within this slow slip area. The largest slow slip, this is the seismic reflection line here. This is the area of largest slow slip event right here where my cursor is. We have a lot of high amplitude reflectivity along the plate boundary, and this has been interpreted as possible underplated, very fluid rich sediment. So it's also likely that there's a substantial role that fluid overpressure plays in these slow slip events. To really get at this, though, we undertook in the last, in late 2017 and 2018, International Ocean Discovery Program drilling on a transect across the plate boundary to really try and, as one of the goals, to try and ground truth some of the rock types that are actually involved in this shallow slow slip behavior. So this is just a bit of an overview of the Iudp expedition aims. And they're really the goal was to really evaluate the mechanisms behind slow slip at subduction zones. So we did this, our transect of sites constituted 2 sites on the subducting plate out here to the right. So this is the plate boundary here. And then this is the subducting Hikarangi Plateau. And the purpose of that is, these are the rocks that are being transported into the slow slip source region. And we're very close to where the slow slip events start right here. So this provides a unique opportunity to really look at the protolith rocks for what the rocks that are the protoliths for what are going into the slow slip zone deeper down. So, and then we had 2 sites on the overriding plate where we installed subsea floor observatories, borehole observatories that I'll talk about in a minute to monitor changes in strain and changes in fluid flow processes and temperature throughout the slow slip cycle to get a much higher level view of what's happening during these slow slip events. And we also drilled through this major active splay fault near the deformation front to really try and characterize the properties of the fault at very close to the surface, the major faults that are accommodating plate motion there. So I'll just show you some results from drilling the subducting sedimentary sequence. So as the concept behind this is, you can see the main plate boundary fault, the décollement right here, and it's basically forming in the lower part of the sedimentary sequence that's overlying the Hikarangi Plateau. Phil Barnes has done a lot of work to tie the seismic imaging to the Iudp drill sites to really pin down the intervals in the sedimentary sequence where this is happening, where the décollement forms, and this is in this blue shaded area. So I've shown on the right, these are lithological logs and some of the additional physical property data that we collected and also photographs of the cores. And the lower part of this drill site 1520, this blue shaded area is the area where we think the décollement's forming. And the types of lithologies that we encountered there was actually a really large mix of different rock types, ranging from carbonate-rich pelagic material to mudstones, a large amount of volcaniclastic sediments and basalts. So we have a very diverse array of lithologies that are actually entering the slow slip region and likely composing that slow slip fault that are really suggesting that that rheological and lithological heterogeneity may also play a very important role in shallow slip occurrence. Basically by juxtaposing, lots of different rock types with various types of frictional properties. So we also, as I mentioned, installed subsea floor observatories above the source of these shallow slow slip events, one through a major active splay fault near the deformation front. This is just that site in the seismic line here. This is the splay fault, Papaku Fault. And then another one further landward above the heart of the large slipping patch of the slow slip zone. You can also see that these two sites are straddling the subducted seamount. So the insights from the observatory will also be able to tell us a little bit about the influence of that seamount on the slow slip event behavior. We have a few different types of measurements going on. I think the most important one from just a monitoring the slow slip events point of view is we're measuring pore pressure down the hole. We have hydraulic lines running down the outside of the casing that are conveying fluids from the formation to pressure sensors on the wellhead. And this is allowing us to measure changes in pore pressure through time continuously. And that's a proxy for volumetric strain, because as you can imagine, if the rocks get contracted during the slow slip event, you're going to increase your pore pressure, or if they're in an area that undergoing extension, then the pore pressure will decrease. We also have fluid flow meters and fluid samplers, these osmo samplers, to look at changes in fluid flow and the hydrogeology during the slow slip event cycle, and also temperature sensor strings down the hole as well to look at fluid flow, also get a better handle on the thermal regime and so forth. Okay, so the last thing I'm going to talk about is the importance of the properties of the upper plate in the slow slip processes as well, particularly in terms of dynamic, sort of long distance triggering of shallow slow slip events. One of the most interesting and sort of unexpected things we've observed from slow slip events at the at the entire Hikarangi subduction zone really is that in 2016, the magnitude 7.8 Kaikota earthquake triggered slow slip over much of the Hikarangi subduction zone. For those of you who don't know, the Kaikota earthquake was a magnitude 7.8 earthquake down here in the northeastern part of the South Island at the far southern end of the Hikarangi subduction zone. Immediately following the earthquake, we had large slow slip triggered. If I can find my cursor, there we go. Up in this area, it was actually initiated up here. This was the area of the Hobbits Experiment in the shallow slow slip area. And then that propagated to the south over a few weeks. We also triggered some of our deep slow slip areas and also had some after slip on the deeper subduction interface closer to the earthquake. But one of the curious things about this is we also found that the ground motions in this area where the triggered East Coast slip was initiated was very, very, very long duration. So this is just showing records from close to the Kaikota epicenter at the bottom of the plot. You have ground motions lasting about 100 to 150 seconds in most of the North Island. However, when we get up to this northern area in here, the ground motions increase to in some places more than 450 seconds. So there's something really different going on that we feel like is probably playing a role in this dynamic triggering. So Yoshi Kaneko has looked at this again in some more detail last year in a JGR paper, and he really needed a very large, very low velocity VS of less than 1.5 kilometers a second to reproduce this very long duration ground motion. And this likely represents the sedimentary wedge, that upper plate, the outer forearc, that in this case is very low velocity and has led to this ultra long ground motion. So we feel like this basin effect from this wedge, this effect really amplifies, and it also increases the duration of dynamic stress change on the interface, leading to the triggering of immediate triggering of slow slip from this, what was a fairly distant earthquake. This area is about 600 kilometers away from the Kaikota earthquake. So we think that this overlying plate plays a big role in it. Okay, so in conclusion, our seafloor geodetic studies are really indicating slow slip event occurrence to within about less than 2 kilometers of the seafloor. The highest slow slip patch appears to occur where there's underplated and subducted sediment interpreted from the seismic reflection data, suggesting that fluids may be playing an important role in these processes. From the seismic imaging and the scientific ocean drilling, those seem to really suggest that the shallow slow slip zone at northern Hikarangi is really characterized by a compositionally, rheologically, and geometrically heterogeneous plate interface, which may be playing an important role in the dynamics of shallow slow slip here. And also the last point is really that we think the elastic properties of the overriding plate are very important to consider and may exert a very strong influence on triggering of slow slip by these more distant earthquakes. And just watch this space, because there's been a lot of really exciting experiments being done by a range of people around the world focused on the Hikarangi subduction zone, and a lot of exciting results will be coming out from these folks over the next few years. So watch this space. So I'll move on to Emily.
Cool. Thank you very much, Laura. So hopefully you can see those slides now, okay? Cool. Okay, well, thanks very much, Laura, for that fantastic overview of the Hikarangi subduction zone and the slow slip events that we see here in New Zealand. I'm going to be taking a little bit more of a seismological stance on this, talking to you about some of the work that I've done as part of my postdoc at GNS Science, and the other work that we've been doing in collaboration with a whole host of different institutions, people here in New Zealand, Victoria University of Wellington and GNS Science, looking at what seismology can tell us about the pulsing of these slow motion earthquakes in the Hikarangi. And there's a lot of outstanding questions regarding slow slip events. Laura's talk has sort of hinted at a few of the major, understandings that we've made in the last decade, but there's still a lot that we don't understand about these events. And some of the questions that are still outstanding in my mind, and particularly from a seismological point of view, is what is it that actually controls the timing of the slip? Why are these events episodic? And why are their inter-event times, their recurrence intervals, much more frequent than for regular earthquakes? And thirdly, can we begin to exploit the frequency and the regularity of these slow slip events to try and make observations of fault zone and crustal property changes in order to understand what it is that actually drives these subduction megathrusts to failure? And that last point is particularly interesting because for other fast slip events on subduction zones, we often miss the opportunities to capture what's actually happening on the fault before it failed. Whereas, the frequency and the regularity of these slow slip events allows us to study multiple slip cycles over a relatively short period of time in order to try and get at the processes that are controlling that pulsing of the slow slip in these places. And in particular, we're trying to understand how fluids influence, interact with, or also respond to slip on these subduction megathrusts. And there's a lot of evidence now globally to show that slow slip event occurrence is related to the presence of high overpressure, so near lithostatic pore fluid pressures, both within the interface shear zone and within the downgoing, the subducting oceanic crust as well. And these fluids can be sourced from a variety of different mechanisms, including metamorphic dehydration reactions, underplating of sediments, or deep hydration of the oceanic crust through downwards pumping of fluids into tensional fracture zones as the slab is descending. And we know that there are fluids down there because seismologically we can observe them through things like high VPBS values, that's the ratio of the P to the S wave velocities, and Poisson's ratios in the oceanic crust. And for that fluid pressure to be maintained, it's telling us that it has to be capped somehow by some sort of low permeability barrier, such as the interface shear zone or the overriding accretionary prism at shallower depths. So we know that there's this spatial relationship between elevated fluid pressure and slow slip, but what we want to try and understand is, well, is there actually a temporal link? If those fluids are there all the time, what is it about those fluids that actually trigger this slip and control their episodicity? Because fluid pressure probably isn't a temporally static feature in these subduction zones. Fluids are constantly migrating and influencing the stresses within the surrounding crust. And we know this because we've got evidence for fluids, for example, being drained into the upper plate following large subduction zone earthquakes, but also now following slow slip events as well. So for example, this study from the Hikarangi Trough in Japan shows this repeated draining of upper plate seismicity swarms following fluid drainage above a slow slip patch on the subduction system. And this process has been commonly described using a valving type model, whereby you can basically think of the plate interface shear zone as being this permeability barrier, which when slow slip or an earthquake happens, it breaks, it fractures, it increases the permeability, and it can act as this seismic valve and basically allow these hydrothermal fluids to drain across it and migrate upwards. And this figure on the bottom right is just kind of showing the schematic version of that. And then the idea of this valving is that these fluids are basically allowed to circulate. Eventually, mineral reprecipitation processes occur and reseals the fracture networks, reduces the permeability again, before the process then repeats itself. So this valving model is basically a cyclical model which links permeability with fluid pressure and fault slip through time. And a lot of work has been done on this by Rick Simpson. And the model basically tells us that fluid pressure, we expect it to be at its maximum or its peak right prior to slip, before that fluid pressure drops during the co-seismic period and following slip, before it then reaccumulates again as the process, the system is resealed in time for the next event. But of course, trying to monitor this process actually happening at depth in subduction zones is quite difficult. Taking in situ measurements of these effective stresses and these fluid pressure values is only really possible at very shallow depths through drilling efforts, some of the examples that Laura showed. So we need to begin to really rely on geophysical proxies, and in particular seismological proxies, in order to try and identify this cycling of fluid pressure and this valving process happening in near real time during these slip episodes. And one data set that we have in abundance in the Hikarangi margin to help us with this is the microseismicity that accompanies these slow slip events. So thanks to some of the fantastic recent offshore deployments of ocean bottom instrumentation, as well as the onshore permanent network that we have here in New Zealand, has enabled us to basically map out thousands more earthquakes, micro earthquakes of really small magnitudes than we knew about previously. And with the improved offshore coverage, we can map them out in a lot more detail and a lot more accuracy. So by looking at where those earthquakes happen and what the orientations in particular of the focal mechanisms of these earthquakes are, we can learn something about the stress field that's actually driving those faults of particular orientations to fail as these microseismic events. And in particular, we've been thinking about how changes in the stress tensor can be caused by temporal variability in fluid pressure, as we'd expect in this valving type model. So in its simplest form, fluid pressure basically acts to reduce the normal or the clamping stress on fractures. And so if you increase the fluid pressure, you can basically broaden the range of fault orientations that are then able to slip. They satisfy this reactivation criteria. And so with increasing fluid pressure, there's an anticipated shift in the style of faulting that we would expect to observe under different fluid pressure levels. So in the example here, which is relevant for the subducting Pacific plate within the Hikarangi, it might be that we see a change from dominantly normal faulting from, for example, with tightly clustered compressional p-axes of these focal mechanisms, to, with increasing fluid pressure, to a mix of both normal and strike slip faulting occurring with this more broad distribution in the p-axis orientations. So by looking for temporal changes in the faulting orientation distribution, we could potentially identify changes in fluid pressure. And this is one of the proxies that we've been developing to look for these kind of processes happening. There's also a few other processes that could produce a similar effect, however, so we've also been using this value called the stress ratio, or the R value, which really simply just describes the relative magnitude of the three principal effective stresses, sigma 1, sigma 2, and sigma 3. And is a parameter that we can also calculate through focal mechanism inversions. And usefully, R has been shown to have this really strong negative correlation with fluid pressure based on observations in geothermal settings during wastewater injection periods. And so it basically offers another proxy for us to try and examine alongside this faulting orientation distribution pattern to help constrain changes in fluid pressure within the system. We're also able to use other seismological techniques that other people here in New Zealand and other groups worldwide have been developing, such as receiver function analysis, ambient seismic noise, looking for variations in velocity, as well as shear wave splitting techniques. And I'll talk a little bit about some of those methods later on as well. So Laura has introduced the Northern Hikarangi subduction system and the characteristics of the slow slip events there for us earlier in her talk. And this is a really great place for us to try and observe these temporal changes in fluid pressure and stress happening during slow slip, mostly because it hosts these slow slip events and as well as smaller transients several times a year. So we've got relatively short observation time periods that mean we can catch multiple slow slip cycles during these ocean bottom deployments, for example. And specifically, we're going to be focusing on 4 slow slip events that happened in late 2014, early 2015, that were captured by the Hobbits Experiment. So we have 2 larger slow slip events, SSEs 2 and 3, and then these 2 smaller transients, number 1 and 4 as well. And the figures on the right here are now just showing the geodetic slip inversions for those events. We can see that there's some overlap in some of these regions. The two largest events here shown on the left and the two smaller transients here on the right. And what we've been doing using the Hobbits data is basically calculating focal mechanisms for as many events down to about magnitude 1.8 as we can. Most of the seismicity here happens within the downgoing plate. So that's where we're going to be focusing our stress inversions. And they're dominantly composed of normal events, which strike margin parallel. But we do also see strike slip events that have their compression or p-axes aligned margin parallel as well. And the average stress orientation within this part of the system is quite nicely defined as this normal faulting type stress field with subvertical sigma 1, your maximum compression, showing that there's extension going on within the slab that's controlled by that tensional slab pull as the slab is subducting. So what we wanted to do is take this focal mechanism distribution and see whether we could observe a change in faulting styles through these slow slip cycles that we might anticipate with the valving model. And we were really nicely surprised by the results once we started getting into them. So you can see here the distribution of the P and T axes for our focal mechanisms during periods at the start of these slow slip events and then at the end of the slow slip events. And you can see that there's a much wider distribution in the P axes happening at the start with this mix of both normal and strike slip faulting happening, whereas at the end of the slow slip events, it's dominantly normal events that are happening. This is also reflected in the stress inversions as well. We can see that at the start of slip, we've got this smearing out between the intermediate, sigma 2, and the maximum compressive stress directions, which is telling us that those two magnitudes are getting much closer in magnitude. So they're much harder to differentiate with the inversions. Whereas at the end of the slow slip, we have this much more nicely defined triaxial stress field with all of the axes much more discretely oriented. So the other parameter that we can look into is this stress ratio and see how it changes with time. And again, this result was really quite striking and pleasing for us when we found this. So this is just showing the variability that we recorded in this R value through time. So the colored bars at the back here are just showing the timing of those slow slip events, and just concentrating on the red line here, which is showing the best fit for the R value with time. And you can see that there's quite significant variability in this R value, varying by about 0.6 throughout this time period. And the main features here is that we can see that there's actually minimas in R happening right at or just prior to the onset of all of these slow slip events. And then the R value basically seems to increase over the course of each slow slip event before it decreases again in between the slow slip. So remembering that these R values are negatively correlated with fluid pressure, this is basically showing us that we seem to be observing peaks in fluid pressure right prior to the onset of slow slip within the downgoing plate. And this fluid pressure then seems to decrease during slip before it increases again during the inter-SSE period. And again, this matches with our faulting style changes too, where we saw this wider variety of faulting happening when the R value is low. So another indicator for high fluid pressure. And if we go back now to the predictions for that evolving fluid pressure, which are made by the interface valving model, our observations actually seem to fit really nicely. So just to summarize, what we think is happening is basically during the inter-SSE time period, the lower plate fluid reservoir is being contained by this sealed interface shear zone. And that's driving up this near lithostatic fluid pressure and these low R values. And we're observing that as this mix of both normal and strike slip faulting within the downgoing plate. Eventually, the high fluid pressure may then trigger the slip, or the slip is triggered by another process and allows the fluids to be released. That impermeable interface barrier is basically breached, and the permeability of the system increases. The R value can then increase, and we get this decrease in the strike slip behavior as they become less favorably oriented. Eventually, then we get mineral reprecipitation from those circulating fluids that reseal the interface and drive the fluid pressure back up again in the fluid reservoir, ready for the next event. And this valving type model is being supported now by a lot of other seismological methods using the Hobbits data that have since been developed since our paper was published last year. And what we're seeing is actually a remarkably consistent story from lots of different independent methods in different parts of the subduction system as well. So the plot on the right here, the top figure is now showing those R values, but I've flipped them over this time just so that fluid pressure is now going up, increasing fluid pressure, just so it's a little bit easier to compare with these other work shown below. And then below it, I'm just comparing it with some of the other temporal variations that we've now been mapping, including changes in the seismic velocity using ambient noise analysis done by Weiwei Wang, a PhD student at Victoria University, and also travel time derived VPBS, and delay time from shear wave splitting measurements done by Hubert Zal, again from Victoria University. And these methods are most sensitive to the upper plate versus the lower plate sensitivity for our study. So it's meaning that we're able to compare the different parts of the system. And I think you can agree that the results are showing some really nice correlations between the independent methods. Weiwei's results in particular, we're seeing changes in her velocities at about the same time and magnitudes that we're seeing in our R values. And Hubert's work as well is showing these precursory increases in fluid pressure and decreasing fluid pressure happening during the SSE periods. So again, these observations seem to be consistent with this valving type model, this draining of fluids into the upper plate, which we now can observe in both the lower plate and the upper plate as well, using different seismological techniques. We're starting to see similar processes happening in different subduction zones globally as well now. This is some work from Cascadia, from Jeremy Goslin's work. And they basically use receiver functions, which is looking at the travel times of teleseismic events coming in at near vertical angles into receiver stations up above the sites, looking for changes in the scattering behavior of this low velocity layer near the interface, which they attribute to be this fluid reservoir. And they basically noticed that over many, many slow slip cycles, they could identify a clear and statistically significant drop in the seismic velocity, which again, they can attribute to this drop in fluid pressure through a similar valving type model that we think we're observing in the Hikarangi margin. So now we're beginning to get a much clearer picture of when this valving is occurring during the slow slip cycle. We want to try and understand how it's actually distributed along the margin. Is it a diffuse process with fluids kind of leaking out all over the place? Or can we begin to pick out discrete patches where we can identify this fluid valving occurring? And this is important because trying to constrain where these potential sites of fluid valving are means that we can begin to design future targeted efforts to monitor these more localized changes in fault zone properties at a much finer scale, ultimately in a bid to try and understand their physical behavior and their episodicity. So in the last few years, decade or so, there's been a fantastic suite of seismological and geophysical studies along the Northern Hikarangi, which Laura's outlined some of in her earlier part of the talk. And what we're beginning to see is there's actually a lot of self-consistency, and we're beginning to identify some common themes in the role of fluids in slow slip, in particular where the fluids are and how they're distributed at depth along the margin. And so some examples of the studies that we can use to map out the fluid distributions, for example, include magnetotelluric data, which has been led largely by Wibke Heiss here at GNS. That can map out the conductivity distribution, the electrical conductivity on the interface to say something about fluid interconnectivity. We can also begin to look at earthquake swarm sequences, and we've observed, this is during the 2019 slow slip event that Laura spoke about earlier. Right before that event, we observed a series of swarm events within the lower plate, which we think could be evidence for precursory fluid migration within the lower plate that could be feeding fluids towards the interface to help trigger that slow slip event. And also the tomographic data sets, which are utilizing this fantastic onshore and offshore seismic deployment coverage that we have to basically help map out where variations in properties like VPBS are throughout the subduction system to tell us where the fluids might be concentrated. We can also map out processes like tectonic tremor, led by Erin Todd in the last few years, which has been shown to cluster around some of these subducting seamounts beneath the accretionary prism. And they seem to increase in frequency following slow slip episodes, which again, we think could be attributed to fluids being drained into the overriding plate following slip. There's also been observations of burst type repeating earthquakes. So these are earthquakes that we think represent repeated failure of the same part of the fault. They produce really highly correlated waveforms. And again, this has been attributed to diversion of fluids and slip upwards onto overriding splay faults within the accretionary prism. And also we can use things like the distribution of the interface microseismicity as well as another proxy for the presence of fluids. This interface seismicity is triggered by slow slip in many cases, but it's not uniformly distributed through the region of the interface that experiences increased stress, increased coolant failure stress from slow slip events, is much more patchy. And so we think that these clusters of interface seismicity could be indicating regions of the interface that are much more critically stressed. So for example, with higher fluid pressure than other parts of the interface. And as we begin to slot all of these different pieces of the seismological and geophysical puzzle together into one big picture, it's actually producing a remarkably self-consistent story. So don't worry too much about the details of this figure, but it's basically just showing a summary of all of the different proxies that we now have for fluid abundance within the Northern Hikarangi. The different earthquake phenomena that we have shown as the colored circles, they seem to be quite clustered in space, and they show really nice alignment with where the BPBS values tells us that there's elevated fluid pressure, shown as these dark pink regions. They also correlate quite nicely with these darker gray regions, which is where we think we have high fluid concentrations derived from the MT work. And also the presence of thermal springs within the overriding plate as well at the surface, which exhibit mantle helium isotope signatures as well, which we seem to think are indicative of some of that lower plate fluid being drained up and reaching these thermal springs at the surface. So what we're proposing really is that these patches along the margin could represent these regions of increased hydrological coupling between the lower and the upper plates. And these fluid-rich zones within the oceanic crust could basically be acting as fluid conduits, which are helping to transport these fluids towards the interface, where they can contribute to this valving process and begin to leak fluids up into the upper plate during this valving process. So here's a kind of schematic overview of the sort of model that we're proposing for this part of the system. It really seems like this valving process could be quite discretely distributed throughout the margin, both along strike and down dip. And it may be able to help explain not just the temporal behavior of these fault zone properties that we can observe through our seismological proxies, but also many of the spatial patterns in terms of seismicity and crustal structure within the Northern Hikarangi as well. And we're hoping that in the next couple of years or so, we'll be able to begin to constrain these processes in even more detail. There's a fantastic opportunity coming up late 2021, so next year, for an upcoming slow slip event in Porongahau. So this is now looking at the central part of the margin, where there's slow slip events here that happen about, almost like clockwork every 5 years or so. And they're really nice, big, discrete events, and they have a lot of accompanying seismicity with them, which means that we're going to be able to really nicely map out the fault slip during these slow slip events using some offshore pressure data sites that we're going to be deploying, as well as some OBS instruments, to get much cleaner signals than what we've been working with in the Northern Hikarangi, where we're battling against lots of these smaller transients happening at the same time as some of the bigger events. So the plan is really to try and capture the precursory phase, or as much of it as we can, for this anticipated slow slip event next year. We're actually starting the cruise component of this in a couple of weeks' time. We'll be deploying the first of these OBS sites offshore from Porongahau. And then hopefully in a few years' time, we'll have what will be really this unprecedented detail of seismological and geodetic data to help constrain the pre-seismic, the co-seismic, as well as the post-seismic deformation signals and changes in fault zone properties during this slow slip cycle. Okay, and then just to summarize this more seismological side of things, so we're beginning to develop now some passive seismological techniques that are proving to be really powerful proxies for spatially mapping and also temporarily monitoring variability in stress and fluid pressure in slow slip hosting regions. Observations from some of these studies are beginning to reveal quite exciting independent evidence for temporarily evolving fluid pressure linked to slow slip event occurrence, which we can explain through this valving type model across the megathrust. And this is offering some really exciting opportunities to help monitor precursory phenomena to try and understand how these megathrust faults fail. We're beginning to see spatial heterogeneity in the microseismicity and the crustal structure, suggesting that this valving process is not spatially uniform. And this means that we might be able to design targeted monitoring efforts to help understand these processes in the future, to try and improve the spatial and the temporal resolution and help clarify the role of fluids versus other processes such as tectonic loading and driving the episodicity of slow slip. Thanks.
Super, thank you very much, Laura and Emily. That was very interesting. So we have various questions in the Q&A. I will start reading them through, and I'm sure you can work out how to answer them between you. So if we start with a reasonably sort of straightforward question, if you could just explain the main difference between aseismic slip and slow slip. And there's a related question about how slow is slow and whether there's a spectrum all the way from aseismic to fully seismic slip.
Do you want me to go for that, Emily, or?
Yeah, sure.
Yeah. So slow slip events are really largely aseismic. I guess that there's sort of types of aseismic slips. Some of, some kind of the more traditional ones we think of is just steady, ongoing aseismic creep that goes on for many, many years or decades or more. But these slow slip events are essentially episodic aseismic slip events. However, we do know they're not totally aseismic because, depending on the slow slip area, there are various flavors of seismicity that occur during these events. So they're not totally aseismic. The larger amount of the moment release in them does occur without seismicity. And in terms of what was the second part was how slow is slow?
Yeah.
Yeah. So it ranges. It sort of really spans, a spectrum. Some of these North Hikarangi events we see, up to 20 centimeters of slip over a couple of week periods. So you could be looking at centimeters per day. But then some of the really longer term, really slow events, particularly the deep events that we see at Southern Hikarangi, also some of the really long-lived large events in Mexico and other subduction zones, you're looking at, potentially tens of centimeters of slip over a year or more. So potentially very, very slow. So there's a big range. And then I think there was also the additional part of that question was, is there a spectrum between the slow slip and seismic slip? And I personally think there probably is. In terms of really defining that full spectrum, we're kind of butting up against some observational limitations because with geodetic techniques, you can see identify transients of certain sizes, over certain periods of time. And then seismologically, you can, see things on the faster end of the spectrum, but there's a little bit of an observational gap there that doesn't allow us to fully see that full spectrum. But I suspect that there probably is a full kind of continuum. And there are some techniques, for example, strain meters and other types of instruments that are starting to help fill some of those gaps. But yeah, that's an observational challenge for sure.
Super. And another question, how can a region undergoing slow slip also fail seismically to produce a tsunami? And what causes the transition between the two rupture regimes? Emily, do you want me to answer that or do you want to go for it?
Yeah, no, go ahead, Laura.
Are you sure? Okay. I think those were the earlier questions from the. Yeah, so what, a lot of people are starting to realize by doing rock deformation experiments on materials that may be involved in slow slip, and also modeling studies, is that the frictional properties of rocks in slow slip zones are probably straddling the transition between seismic slip behavior, what we call velocity weakening behavior, versus sort of aseismic behavior or velocity strengthening behavior that doesn't support earthquakes. So given that we're in that transition, I think you can easily see scenarios where you could potentially change your physical conditions or potentially have a push, a nearby earthquake or something that could push you more into that velocity weakening sort of regime. And so I think that the fact that we're in that transition also, makes it possible to have seismic slip in these areas. And tsunami earthquakes, these really strange tsunami earthquakes, that not very big earthquakes that cause large tsunami, are a bit of an enigma, but a lot of particularly studies of the New Zealand ones, the 1947 ones, suggest that they have a very, very slow rupture propagation compared to other kind of normal earthquakes. And there's also been a lot of other studies that have suggested that perhaps these tsunami type earthquakes are also occurring in a kind of conditionally stable frictional regime. So there may be a sort of linkage, spatial linkage between these tsunami earthquake type behavior and the shallow slow slip events. And I don't think we can actually rule out, potentially having more normal, big magnitude 8 events in some of these shallow slow slip event regions either. I think we need a lot more observations of these things globally.
So to know what that relationship between slow and seismic slip is.
The next question comes from Steve Hicks. Have you looked for similar changes in seismic observables that you see around the shallow slow slip events like R-value changes and VPBS changes for the deeper onshore slow slip events beneath the southern part of North Island of New Zealand? And if you haven't looked yet, do you think that such changes would be as obvious as they are as the ones that you're dealing with under North Island?
Yeah, that's a really great question. The answer is no, not yet. We haven't looked. One of the difficulties is that those events are much less frequent than we have in the Northern Hikarangi. So some of the temporary deployments, for example, the seismic deployments that have been out haven't covered that kind of full slow slip cycle. Like we have to have a much longer observation time period to potentially see those changes happening. It's kind of on my long-term to-do list is to begin to look for similar things in that part of the system as well. From a focal mechanism point of view, they might not be quite so obvious. One of the reasons that the stress ratio value works so nicely in the Northern Hikarangi is that we have this mix of both strike slip and normal faulting going on within the downgoing plate. Don't think that's so much of that mix of faulting is really observed so much within the downgoing plate in that deeper part of the system. So it may be that our methodology, for example, our proxy wouldn't be applicable so much in that part of the system. But yeah, you're right. Looking for changes in VPBS, for example, would be a good thing to try and do in that part of the system. Yeah. Super.
We have reached 4 o'clock, but there's plenty more questions if you're happy to keep going for a little bit longer. Excellent. Yeah. So the next one comes from Tim Reston. I think it's a really good question. As to whether or not the fluids moving up out of the oceanic crust correlate with the closure and unbending of bend-related faults formed near the trench.
Yeah, so maybe I'll answer that one again. So yeah, I think you're right. One of the major sources of fluids within that downgoing plate is these extensional faults, tensional faults that are formed as the slab begins to bend and become subducted, and the fluids then begin to get basically downwardly pumped into that deep part of the oceanic crust. And as that plate is then subducted, we think it's probably those major fault systems, those tensional bending related fractures that are potentially acting as these fluid conduits for the fluid being released up into the upper plate. And that kind of spatial heterogeneity that we're seeing could be related to, regions where we've got increased bending related tensional fractures within that part of the downgoing plate, or it could also be related to, these subducting seamounts that we see basically being, regions where we can actually get that increased hydrological coupling between the two different plates. And Laura showed, we've got this really rough incoming, Pacific plate coming into that part of the system, and how that heterogeneity might influence then the heterogeneity of the fluids actually being able to be released into the upper plate.
Super. Then a question from Rich Katz. Since pressure changes are implicated in slow slip events, do the GPS inversions include a poor elastic model when they constrain the slip distribution? And should they, if they don't? And does the GPS signal contain information about the pressure redistribution itself?
Yeah, so we don't include poor elastic deformation in the GPS in the inversions. I suspect that it's probably not going to play a big role, particularly with the onshore GPS. But I think, when we get to interpreting the pore pressure changes that we observe from the subsea floor observatories, I think this is, something that we potentially, want to consider in that. And then what was the second part of the question?
About whether or not the GPS signal itself contains information about the pressure redistribution.
Yeah, so I think it's because you're so far from where the slow slip is happening with the GPS. I think it's actually, we have a difficult time imagining that the GPS is saying much about the pressure redistribution, with the exception of the fact that, as Emily's pointing out, that perhaps that fluid pressure redistribution may be influencing things in the slow slip cycle. So we may be seeing the kind of symptom of that, but I don't think we'd actually be able to observe deformation specifically related to that because we are so far from the slow slip events. But again, the borehole observatories that we've installed in the near field of the slow slip area will give us additional, observations from the pore pressure changes, temperature changes, and also fluid flow rate changes and so forth, that it's going to give us some more information on the hydrogeological changes that occur through the slow slip cycle. And I also I didn't get time to mention, but during the 2019 slow slip event, there were actually a suite of seafloor flow meters out during that event as well that Evan Solomon from the University of Washington had out. And we're going to go recover those in March in a few months. And so that's also going to give us more insight into the hydrogeology, the influence on the hydrogeology of these slow slip events and the interplay between slow slip events and fluids and seismicity as well. So it's actually a pretty exciting opportunity to be able to look at these things, having all these co-located observable seafloor geodesy, OBS, borehole observatories, and seafloor flow meters. So
great. And then we'll wrap up with one last question from Jess Hawthorne, which is a two-part question, asking firstly if you could explain one more time why increasing the pore pressure makes sigma 1 minus sigma 3 closer to sigma 2 minus sigma 3. And secondly, whether the pore pressure change is large in terms of spatial extent on the order of kilometers or tens of kilometers.
Yeah, thanks, Jess, for the question. So I'll just go back to sharing my screen and use my extra slides, which have come in useful. So yeah, this negative correlation between R and fluid pressure is kind of an interesting one, and it's sort of comprised of two components. The first is that it is simply probably partly a method artifact. So the observations from this geothermal study by Martinez-Garzon et al. Basically showed that it probably doesn't have a physical basis. It's basically when you have this broader distribution of faulting happening, it changes how well sampled the fault orientations within the stress state are. So you're basically less able to resolve the value of the correct fault plane that's slipping in those circumstances. So you have this negative correlation, but it's not a physical basis, but it is a useful negative relationship nonetheless. The other idea is that it's actually related to anisotropic pore elasticity, which is a phenomenon that I don't really understand very well, and is actually there's not a lot of literature out on it, basically. David Healy has done some of this work in his 2012 paper, which I'd recommend going and having a read of. And the idea is basically that if you have an anisotropic system, pore fluid pressure doesn't necessarily act the same in all directions. So if you think about an isotropic system, you increase fluid pressure, you're basically decreasing all of your effective normal stresses by the same magnitude. But if your fluid pressure acts differently in different directions under this anisotropic state, then you can basically get, well, in this particular instance where we have this anisotropic subducting plate, which is the anisotropy is really controlled by these tensional fractures within the downgoing plate, and we know that the stress field looks something like this normal faulting type stress field, then you basically get a larger decrease in your sigma 1 and your sigma 3 effective stresses with increasing fluid pressure than you do in your sigma 2 direction. And so that could therefore be this physical explanation for why you get this change in the R value, because you're basically changing the shape of the Mohr circle, the shape of the stress tensor, by changing the fluid pressure differently in different directions.
Super. There are a few more questions, but I think we're sufficiently far over that we should probably end it there, let you go and find some more coffee, given the time of day it is in New Zealand. Thank you very much once again. Can we all thank our speakers? We'll have another seminar in 2 weeks' time, which will be from Professor Jennifer McAlady from Penn State in the US, who will be talking with a title that is yet to be confirmed, but will be probably something to do with life in extreme environments. Please check out the webpage and the Twitter feed for further information on upcoming seminars. Thank you once again. Thank you very much.